to all our seniors, Professor Dinakar sir, our HOD, who is also the faculty advisor of our OPTICA student chapter, respected faculty members, and our today's guest, Professor Andrew M. Wiener. SPIE, the International Society for Optics and Photonics, serving up to 255,000 constituents from 183 countries, is a not for profit society whose goal is to provide community services, conduct events, conferences, career development, and training programs. Is honored to have such an innovative and enthusiastic mind in our today's talk. Optica, formerly OSA, the Society Advancing Optics and Photonic Worldwide, is a leader of excellence, delivering high-quality scientific and technical information that is objective, accessible, and accurate. The new brand, Optica, builds on our history of discovery and innovation. Since 1916, the Society has been the world's leading champion for optics and photonics, uniting and educating scientists, engineers, educators, technicians, and business leaders worldwide. Optica currently serves 432,000 customers from 181 countries. The purpose of the talk is to inspire all the bright minds and thinkers who find enthusiasm and interest in understanding light and its applications. The topic on which today Professor Wiener is going to deliver his words is signal processing at light speed, ultra-short optical pulse generation with our arbitrary waveforms. Moving on with the event, it's time to invite our speaker, Professor Andrew M. Wiener, who is the Skyforce Family Distinguished Professor of Electrical and Computer Engineering. He is a member of the US National Academy of Engineering and of the National Academy of Inventors and was selected as a Department of Defense National Security Science and Engineering Faculty Fellow. Professor Wiener presently serves as Editor-in-Chief of Optics Express, an all-electronic open access journal publishing more than 3,000 papers a year, emphasizing innovations in all aspects of optics and photonics, and previously served a third-year term as chair of the National Academy's US Frontiers of Engineering meeting. After Professor Wiener earned his doctorate in science in electrical engineering in 1984 from Massachusetts Institute of Technology, he joined Bell Corps, at that time a premier telecommunication industry research organization, first as member of technical staff and later as manager of ultrafast optics and optical signal processing research. He joined Purdue as professor in 1992 and has since graduated close to 40 PhD students. Professor Wiener has also spent sabbaticals at the Max Born Institute for Nonlinear Optics and Ultra-Short Pulse Spectroscopy, Berlin, Germany, and JILA, University of Colorado, and National Institute of Standards and Technology, Boulder, Colorado. Professor Wiener's research focuses on ultra-fast optics with a focus on processing of extremely high-speed light wave signals and ultra-broadband radio frequency signals. He is especially well known for his pioneering work on programmable generation of arbitrary ultra-short pulse waveforms, which has found application both in fiber optic networks and in ultra-fast optical science laboratories around the world. Professor Wiener is author of a textbook entitled Ultra-Fast Optics, has published 11 book chapters, over 300 journal articles, and over 500 conference papers, and is inventor of 18 US patents. In past years, he chaired the Conference on Lasers and Electro-Optics, the International Conference on Ultra-Fast Phenomena, and the Jordan Research Conference on Nonlinear Optics, and has served as treasurer on the board of governors of the IEEE Lasers and Electro-Optics Society. His numerous awards include the Hertz Foundation Doctoral Thesis Prize, the Optical Society of America's Adolph Lomb Medal and R.W. Wood Prize, the International Commission on Optics Prize, and the IEEE Photonics Society's William Stryfer Scientific Achievement Award and Quantum Electronics Prize. At Purdue, he has been recognized with the inaugural Research Excellence Award from the Schools of Engineering, the Provost's Outstanding Graduate Student Mentor Award, the Herbert Newby McCoy Award for Outstanding Contributions to the Natural Sciences, and the College of Engineering Mentoring Award. Now, I would like to invite Professor Wiener to enlighten us with his knowledge, experience, and words. Sir, please go ahead.
Yeah, okay, great. Thank you. So I haven't, used Google Meets, but it looks like it shouldn't be too hard to share. Okay.
The arrow symbol, sir. Just you press the arrow symbol.
Yeah, I think I've got it,
Yeah.
but let's see.
I mean,
Okay, so do you see my correct PowerPoint screen?
yes, it is visible, sir.
Okay, good. All right.
Both audio video are clear, sir. Both audio video are very much clear.
Yeah, okay, that's fine. Okay, so yeah, it's my pleasure to give this seminar on ultra broadband optical signal processing. What the where's the pointer? Okay, no pointer. All right. What the cover picture is really sort of an artist's conception of a waveform. Ultrashort waveform, more generally just broadband signals. Techniques to processing signal manipulation and waveform generation. So that's what I'm talking to you about today. Thank you for the complete. I think I probably need to upload not chirping at that to express a few years back. New ledger from the University of Minnesota, but it's very much so I encourage you to commit some of your work. So I'll start with just a very brief introduction to more general. So the network scale electronics as well. It goes to faster seconds. It comes to a range where electronics, technology, access, make measure. There are a number of applications now Photonics, but I can illustrate some of the uses of this plot referring to the process that in particular, in femtosecond chemistry work, as Whale and his group were able to use pulses on 100 femtosecond time scale to initiate and then measure the dynamics of simple photo-induced chemical reactions. Another topic is optical frequency cones. Jen Hall and Ted Hensch shared part of the Nobel Prize in Physics in 2005. And as shown in this picture, the idea is to make very broadband light. In fact, it has to span an octave for some technical reasons. But for pulses coming from a mode-locked laser, the fine structure really is a series of extremely equally spaced delta functions of frequency. And so they and their colleagues showed that this could be used really as an ultra-precise frequency ruler to make precision measurements that have reached sort of 19 digits of precision to compare different frequencies. This is used in frequency metrology, RF waveform generation, and spectroscopy. These days. So this sort of emphasizes really the broadband nature of light, but at the same time the ability to really do ultra high frequency resolution with the right type of systems. And another attribute of short pulses is the ability to make very high peak intensity by packing, whatever average power is available into very short, very intense pulses. And so Gerard Moreau and Donna Strickland most recently got the Nobel Prize back in 2018 for their chirp pulse amplification technique, which sort of involved taking short pulses, stretching them into lower intensity, longer waveforms that could be safely amplified without incurring optical damage and unwanted nonlinearities in the amplifiers, then compressing back to the original duration to reach incredibly high intensities, allow one to sort of use these sort of lasers to measure matter excited to sort of temperatures and conditions that can't be normally made in the laboratory. So my interest in ultra-fast optics sort of evolved into yet another dimension, which overlaps with some of these ideas, but I've been interested really in the information content of short optical pulses. How can they carry information? How can we manipulate the signals? Starting off looking at applications in fiber optics, for example. So that's going to be the theme of this talk, sampling a few activities over a long span of years. And in addition to talking about the signal manipulation itself, we'll touch on some transport of short optical pulses in fiber optics. We'll talk about some hybrid systems involving sort of RF technology and ultra-fast optics, something called radio frequency photonics, and some broadband RF signal processing enabled by photonics. We've also become quite active from 10 or 15 years in, I'd say, nonlinear integrated photonics. Unfortunately, based on time constraints, that's a topic I really won't go into in this talk. And most recently, over a number of years now, we've been working with broadband light in the quantum regime and looking at entanglement and starting to look at applications to quantum networks. And so I will touch on that. So the outline is as follows. I'll have a first major portion of the talk talking about femtosecond pulse shaping, or essentially ultra-short pulse arbitrary waveform generation. As mentioned in the introduction, that's probably the area for which done when I was a fairly young researcher, but for which I think I'm probably best known. And I'll sample, some of the applications. We've been interested in these sort of ideas, taking them to different fields for most of my career. And so I'll touch on dispersion compensation for short pulse and fiber optics in the RF photonics regime, how to use photonics to enhance broadband wireless transmission. And I'll touch on some of our recent activities, and which we have quite a lot of work going on sort of signal processing for broadband quantum optics. So again, we'll talk about synthesizing ultra-short pulse optical waveforms. The idea is this is going to be a Fourier synthesis technique that's sort of analogous to music, where if one puts together different tones, one makes hopefully a pleasant musical result. If we kind of look at slightly more technical depiction, looking at different different frequencies, this picture showing adding 1, 2, or 5 equally spaced frequencies. We start with a single sine wave. We superimpose 2 sine waves, 5 sine waves. Once we do this, we can see that depending how these sine waves are phased, we can find areas where the different sine waves add up nicely. When you add them all up, you start to generate short pulses. So short optical pulses in general are superposition of many, many equally spaced frequencies that are in phase, so they can add up constructively, make isolated very short pulses. Spectral phase will be very important in this talk, and so just to illustrate that in this simple animation, we assume we have 2 cosines harmonically related, omega naught and 2 omega naught, and then we're varying the phase of one of those cosines with respect to the other, and it's smoothly see the cosines matching along. And as we look at how they add up, we can see that the waveform really strongly depends on the relative phases. So much of what we'll be doing in this talk is manipulating optical phase, not just on 2 frequencies, but on a large collection of frequencies, and exploiting that capability. Going beyond, so we're really going to be interested in making waveforms. And this animation is just a classic example from signals and systems type classes, but doing a Fourier series to make a periodic series of square pulses. This is showing sort of one period of such a periodic square pulse. And so what's happening here is we're looking at the summation of 31, DC and then 30 additional harmonics, and we're adding them one by one with proper amplitudes and proper phases to make a square pulse. And so you can see as we add more and more frequencies, we get a better and better approximation to a square pulse. So this is Fourier synthesis. If we look at the instantaneous frequency, one at a time being added, we see that to do this, we have to control the relative amplitudes, but we see some, sort of zero crossings, and that's a phase reversal, applied phase shift. So we would need to be able to kind of control the spectrum both in amplitude and in phase. Okay, and so that's relative, as I said, relatively early in my career. This is a kind of an idea that I, with one close colleague in my Belcourt days, a fellow named John Heritage, we had this idea that we could do this with ultra-fast optics on this very fast time scale, faster than sort of normal electronics, and we would do it in an arrangement like this. So imagine a short optical pulse coming in, say 100 femtoseconds, for example, should have an order of 10 to the 13th hertz, or a lot of frequency content. Send it into a diffraction grating that sort of spreads out the different frequencies according to different angles. Only two represented frequencies are sketched here, but there's a continuous set of frequencies. Use a focusing element to sort of focus on the small spots that are separated. So different frequencies should be separated along a line right here. And at that point, so far this would be how you build a spectrometer to measure the spectrum. But the innovation was to put in a spatially patterned object, which sort of evolved into electronically controlled spatial light modulators, so that we can control amplitude phase on a position by position or frequency by frequency basis. So that's doing the Fourier synthesis. Some more optics puts the beam nicely back together. And at the output, we have a new waveform that's dictated by the inverse Fourier transform of the spatial pattern put onto the spectrum. And these are just some early examples of ultra-fast waveforms where single pulse was transformed into what I like to call a femtosecond data sequence, several pulses that are spaced by a few hundred femtoseconds, or by sort of randomizing the phases, we can actually transform it into something that looks like a broadband noise waveform in a reversible way that can be restored to a short pulse. Okay, so with the use of electronically controllable masked or modulated arrays, this is fully programmable, so you can make user-defined waveforms, and we'll illustrate a few of the broad applications of this technology. In terms of how it looks, this photo is now one from my lab actually about 20 years ago, when we first started to try to combine such systems with fiber input-output, as you can see some of the fiber cables here. But so light comes out of the fiber through a collimating lens. We just sort of sketch in the colors here because it's telecom light, which is invisible. Diffraction grating spreads out the frequencies, a lens. This is a commercial liquid crystal spatial light modulator that allows us to have 128 different control elements. And here, this is kind of built in a folded geometry where mirror sends it back through. It's equivalent to what's shown here in the top left, and we go back into a fiber. For somewhere between 10 and 15 years now, there's been some very nice commercial implementations. These really grew out of the wavelength selective switch technology, which is deployed in the fiber optic network, which itself was a generalization or evolution of this geometry that we had to introduce for pulse shaping. But so with these commercial elements, typically they work in the lightwave C-band, about 5 terahertz of bandwidth. There's a few different options. You can put individually controlled frequencies spaced at 10 gigahertz with about 500 resolvable control elements. So there's very nicely engineered systems, and you have quite a lot of sort of user control. Okay, so let's see some experiments. These are first some early experiments. The first will be sort of a temporal version of Young's famous 2 slit diffraction experiments. So of course, in this well-known experiment, the idea is to take quasi-monochromatic light, send it through either one slit or two spatial slits, and then looking at the far field, one sees a diffraction pattern, which goes as a spatial Fourier transform of sort of this input pattern here. So if we go diffract through one slit, the Fourier transform of a rectangle is a sine x over x or a sinc function. That's what we're going to need to make a square as well. So a peak with some side lobes. And with a two-slit pattern, then we superimpose a fast modulation. So you see this sort of fast spatial beating. And, so using pulse shaping, early on, we were able to do a temporal analog of this. The experiment is shown here. Inside the pulse shaper, we were using kind of fixed mask at that point. And so we had a gold on glass opaque mask with two slits opened up on it. So we could send it through two frequencies. And by the way, with a second mask, we could had a way of tunably putting on a relative phase. We could put in a 5 pi phase shift. So in the red, we have no pi phase shift. We see a fast beating structure. This is a measurement called a ultra-fast intensity optical cross-correlation experiment. But the bottom line is it approximately gets the optical intensity. So you can see the fast beating pattern, which is analogous to the two-slit experiment. But now by putting on a phase shift, we still have two frequencies. They still have to beat with each other. But this phase shift in the spectral domain translates into a sort of shift in the temporal peaks. And we can see that clearly as well. And so already with a very kind of simple kind of idea, one can start to make some complex looking waveforms. Going on to now do the experiment on making the square pulses that I suggested earlier. These are again gold on pattern, gold on glass masks. We're essentially a strong transition center. We have some dark areas, we have some side lobes. The thing on the pulse shape for such mass, a lot of side lobes. We see a strong peak. You can modulate the spectrum down somewhere between 3/4 of the magnitude dynamic range. Identically close to the desired modulation, which is the dotted line. Put in the phase shift on another one as shown here. We can take just like an input pulse, make looking at profiles, which is very close to the target, and with fastest feature rise pulse and the limited by the fastest configuration of the input pulse. Well, also. And the phase, that most of the layers, this is the in the early 1990s, but basically for the layer, it's the layer with the close. It's can be aligned in the part from the translational point of view. You can have some molecules, like molecules, and the molecules are aligned for the direction. They will have a large vacuum index for like up that size, even with propulsion. And now some pattern electrons are transparent, but you have electrons, you get a bench that ground on the inside, and you apply local voltage, you make a electric field sort of that's pointing into the electric crystal layer. It's a thin electric crystal layer. That exerts a torque on the molecules, and they rotate, and they tend to align sort of along the electric field. That changes their orientation with respect to the optical electric field and changes the refractive index. And so you can make a phase modulation that way. With some proper orientations and a sandwich of these, you can do phase and amplitude as well. Okay, this is kind of an early, sort of picture from one of the things we made in the laboratory. And good, so you can do that. They're not particularly fast, so it's limited to around a millisecond. And usually the electrical boxes limit them to tens of milliseconds, but you can have a lot of control elements. And so a fundamental Fourier relationship is that if you apply a frequency-dependent phase, psi of omega, then there's a frequency-dependent delay, we could call that dispersion, that goes as the derivative. And so by making an appropriate frequency-dependent phase, you can manipulate delay. Here's one example. In this early experiment, we put on a linear spectral phase. Derivative of that is a constant. And by going with different linear slopes, we could move the pulse forward or backward in time by many pulse widths with no moving parts with respect to the kind of unshaped case. So this brings us a little bit into sort of the fiber optics. So I got interested. We were at a telecom type laboratory, and fiber optics was still pretty early, but clearly coming. And so we're interested in could we send very short pulses as very short bits of light over fiber? As I think you probably all know, that the low loss region of fibers are kind of very broad. Depending how you define it, you might say there's sort of 10 terahertz worth of bandwidth, and that would support very short pulses at the scale of 100 femtoseconds or less. And so we were interested in, well, how short a pulse could you send over optical fiber? The principal limit really is dispersion. The fact that the velocity of light in materials is frequency dependent, and that's sort of illustrated on this slide. If we look at the pulses, it propagates. You can see it getting broader, and the different colors are starting to spread out. That's from the frequency dependent delay. What we see in these other plots, we see sort of a spectrogram or time frequency plot of the light, and we see that different frequencies are sort of dispersed in time. And from the phase perspective, this is described at the lowest order as a quadratic spectral phase. Okay, so that's dispersion. So we got an interest in experiments like this. Let's send a short pulse over an optical fiber. It spreads out. Now, at this time in the late, by the late 90s, commercial fiber optic systems had reached about 10 gigabits per second. This was starting to be enough bandwidth so that when pulses went over interesting lengths of deployed fiber, say 40 or 50 kilometers, they started to spread a fraction of the bit period, 100 picoseconds, and that would induce errors in the system. So there was a need to have compensating techniques, and dispersion compensating fibers with different waveguide designs were invented. And these dispersion compensating fibers would have the other sign of frequency dependent delay. So that if, as shown here, if the blue frequencies came out later in the first, or earlier in the first fiber, they would come out later in the second fiber, and you can put them back together. So we are interested in the short pulse limits of this. Instead of working 100 picoseconds, could we do this with femtoseconds? The issue is going to be that dispersion has not only quadratic phase, but higher order phase. And so as the pulses get shorter with more bandwidth, we end up with some distortion. And so our idea was that we could fix up whatever phase remained and restore a short pulse. Okay. This again depends on this idea that the frequency dependent delay or dispersion is equal, it goes as a frequency derivative of the applied phase. So I'll show two examples here. In the one of our early experiments, we had a fairly modest piece of fiber, about 3 kilometers of single mode fiber, then with some dispersion compensating fiber, which was experimental at that time. We were able to get a sample from colleagues at Bell Laboratories, and I remember my students stretching on the hallway and trying to exactly trim the length to get it just right. But you put these two lengths of fiber together. We start with about 500 femtoseconds. Not shown, but this spreads in the first fiber about several hundred times. After dispersion compensating fiber, we can bring it back to pretty close, but you can see some broadening and some tail. In this type of asymmetric oscillating tail is a sign of cubic spectral phase, the next highest derivative of phase versus frequency. So in our pulse shaper, we apply a phase versus pulse shaper pixel or equivalently frequency. It looks like this. When we get it right, we completely fix the pulse, and now it's no remaining distortion. So this was it was a long time ago, but this is the first experiment of its type, sending pulses as short over even kilometer lengths of fiber without distortion. Somewhat more advanced experiment 6 or 7 years later, dispersion compensating fiber was now commercially available. You could buy it in modules that would compensate 25 or 50 kilometers single mode fiber. So that's what we did, 50 kilometers. So here, our input's still about 500 femtoseconds. It spreads about 4 orders of magnitude to 5 nanoseconds, the first fiber. With a commercial dispersion compensating fiber box, we can bring it back to this sort of black dotted curve, about 14 picoseconds. It's pretty badly distorted, but it's about 99.7 percent compensated, which somehow is pretty good. But so what we did is now we played with the phase. There's remaining a quadratic phase. We fix that. We get this blue curve. It's almost good. Now there's a little cubic phase. We kind of add that and program that in our pulse shaper. We get this red curve, which is essentially undistinguishable from the input again. So sort of 4 orders of magnitude spreading and compensation. And so ideas like this are used not only in fiber optics, but in the chirp pulse amplifier systems. These sort of techniques are often used to really help you fully compress. One last one I want to show some relatively recently, a few years ago, we were involved in a DARPA project where we had the ability to bring in a company, Infinera, which is one of the world leaders in indium phosphide integrated photonic integrated circuits, and with the idea of making some integrated photonic pulse shapers. So we collaborated on this. Here's just an example of the results. Now, these are now on indium phosphide chips. Imagine light being coupled in to some waveguides. They had an array waveguide grading. Here's sort of a layout. It's essentially light is sort of distributed to a series of waveguides that have different, from waveguide to waveguide, different lengths. This is a well-known component in wavelength division multiplex fiber optics. As a result, you sort of make an integrated grading. When light comes back out, different frequencies of light sort of diffract to different angles. And what we did, we used that to separate out the light. Here's sort of dispersion of different frequencies, if you will. Imagine this is a spatial pattern going to different waveguides. There are 32 waveguide channels here. Each of these was fed to a semiconductor optical amplifier over which we have independent electrical control, so we could play with the relative amplitudes. We couple them back through this to put the frequency back together, so that's like the second lens and grading in a pulse shaper, and out the light comes. And so we're showing here, we start off with this sort of a 32 frequency optical signal. This is made by something called an Electro-Optic comb generator. We have 32 lines spaced by 25 gigahertz, but they're not very flat. There's a sort of a 7 or 8 dB difference in the powers of different lines. So what we can do with this device is we can program the amplitudes. Here we kind of have iterative algorithm for playing with the drives to this array, with the goal of sort of equalizing all the intensities. And so we're able to do that, as you can see in the movie. Another thing we can exploit here is semiconductor optical amplifiers are much faster than liquid crystals. Instead of working milliseconds, they can work approaching nanoseconds. And here we worked at the microsecond scale and simply showed that we could reconfigure this sort of operation on a sub-microsecond scale. And so here's a picture of our 32 lines after equalization. And what we can do is we can very rapidly, in this experiment, we just killed every other line. So now I have 16 lines, now spaced by 50 gigahertz. So originally this is going to be a train of pulses spaced by 25 gigahertz at 25 gigahertz. When we cut out every line, it turns out to a train of pulses at 50 gigahertz. At these frequencies, we can see something on a fast oscilloscope. We can't resolve all the harmonics, so you don't really see the pulses, but you see the periodicity. And what we do is we change the electrical drives, so we rapidly go from the 32-line spectrum to the 16-line spectrum. Using a fast real-time oscilloscope, we're able to sort of take a whole transformation from this waveform to this waveform. And when we plot in different ways, we can see at a sub-microsecond scale, this is showing the frequency content, we're able to transition waveforms. So there's certainly more to be done here, but an interesting way is to use integrated photonics to really push more and more to making these very, very fast and reconfigurable. Okay, let me go on and talk about the two applications. This one's ultra-broad radio frequency photonics. This was an area we've been interested in for some time, but much of the work we were very active on this sort of 10 to 15 years ago, and so you'll see some of that. And so here the idea is that, even though electronics is getting better, if you want to really make fancy, highly structured waveforms at very high frequencies, it's still very hard to do. And so our idea was, and this was particularly true when we did this work really starting 20 years ago. And so the idea was, let's take our short pulses, let's go through an optical shaper, okay, and let's view that as a programmable arbitrary spectral filter. Here's an example. We came with the pulse filling the C-band. We get, sort of all this, highly structured stuff. I'm going to send it through a fiber now, and here we're going to exploit the dispersion I talked about before. It separates different frequencies at different times. You can think of it as a frequency to time converter. It'll stretch our spectrum to the nanosecond scale. Then we'll detect it with a fast photodetector. And so here's an example. You can see almost a replica of the signal, but now it's not in wavelength, it's in time. And so this is making a frequency hop waveform, 5 gigahertz, 2.5 gigahertz, and 1.25 gigahertz within a few nanoseconds. That was beyond what the electronics could do at the time. The electronics has gotten better, but you can do there's a lot of more bandwidth with the optics. So this was an example about 10 years later, where we made a much more complex waveform, where we sweep from 45 gigahertz to about 4 gigahertz over about 8 nanoseconds or so. You can see the different frequency content, which matches very, very closely with the theory. And this is using the same basic technique. It turns out it's more challenging because there's some important details about how the transformation from frequency to time goes that aren't quite as simple as I suggest here. And you really have to sort of master them to get this to work at this level of detail and bandwidth, but it's being done. And so these are making waveforms that are still, what I think, we viewed as extremely challenging to make with electronics instrumentation. So what are some things you can do here? Well, one is working at even higher frequencies. Some years ago, we did a collaboration with Professor Shi in Taiwan, who was making very high frequency photomixers to take the waveform generation to what's called the W band, 75 to 110 gigahertz. So this is even higher frequency. Okay, and so it's the same basic technique, but there's some cool technology. Somewhere in here, there's a little photo mixer chip that can work up to 110 gigahertz and actually beyond. Light is focused in, and this sort of has a little, sort of coupled into a waveguide. And this waveguide is going to take it to an antenna through some. This is the highest frequency, can really get some nice power amplifiers. So we'll amplify it, we'll send it through a transmit antenna, and later on we'll reflect it off some targets and do some essentially radar experiments at 100 gigahertz range. Here's a receiving kind of antenna. So these are some examples of waveforms. You can't see the details. There it's a 35 gigahertz chirp from about 100 gigahertz to 110 gigahertz down to about 80 gigahertz, something like that. Here's the time frequency. So this was really a waveform that's not at all convenient or possible to make with pure electronics. We make a lot of other waveforms. But it's interesting to sort of, couple it with radar. So in radar, you're sending out broadband signals, reflecting off objects, measuring the returns, and sensing distance based on the time delay. And so here in this experiment, we have a transmitted antenna. We're going to send it out, and we have these reflectors. There's a sort of target here that's relatively close, and several kind of metal plates that are further away, and we'd like to kind of measure all their distances by analyzing the delay between the different echoes that we detect here. And here what bandwidth does for you, the inverse of bandwidth gives you time resolution. So at 35 gigahertz bandwidth, you can do some fraction of 30 picoseconds. Okay, and here's an example of the results. So in this sort of experiment here, if we kind of look at the return signals, we can see return signal from the close object, from the far objects. In this case, there's sort of 3 plates here, okay? And we can get about, there's about 50 picoseconds resolution, that's fine. And then what we did is to kind of explore the range resolution with 2 of these plates. We can move them with respect to each other, so we can change their relative ranges by a small amount. And, when we do that and have them slightly different ranges, we can resolve, for example, 2 peaks at, here's a couple of different examples, but even down to about 4 millimeters. And so actually at this kind of frequency range, and then, and I believe this is still true, is sort of the best range resolution that was reported. Of course, it's a laboratory system, but does show, I think, some of the nice potential of these interesting broadband optics and RF kind of combination systems. We can also look at dispersion or things analogous to dispersion. So here, these were really ideas that had been little explored in the RF, but if you come out of ultrafast optics, they're kind of obvious, ideas to explore. So the idea is many antennas are themselves dispersive, or if you hit them with a pulse, they radiate with a frequency-dependent delay. And so here we're using, for example, commercial log periodic antennas. This is a ridged horn, receiving antenna. They're just separated by 1 or 2 meters, and you're kind of pointing at each other, and we time resolve it. So what happens is we generate sort of a 200 picosecond impulse here just by hitting a fast photodetector with a laser as the input to this antenna. And if we look what we measure at the output, you can see it's strongly frequency modulated or chirped. It's stretched by about a factor of 10. That really has to do because of the frequency-dependent delay with which this log periodic antenna radiates. You can figure that out from theory, but let's just sort of leave it at that. So what we can do is after measuring this, we can make a time reverse version of the waveform so that it should get self-compressed in this process. So we shoot this around in time. Here's the laser generated version of that using this pulse shaping technique. Instead of going from high to low frequency, it goes from low to high frequency. When you get it right, and do the experiment, when you measure here at the output, now it's sort of self-compressed. Okay, so that works. We've taken this to sort of factors of 100 compression, which I won't show here, but this is really kind of analogous to some of the optical experiments. Another interesting thing is you can have more complex experiments. So if you do any kind of certainly indoor wireless, the channel is dominated by what's called multipath. So if you imagine sending a short pulse through a transmitter, let's go through a wall. We're going to bounce off the floor, off various objects, and you're going to see a whole series of echoes. Here's some actual measurements. We kind of did this with kind of 10 gigahertz type of impulses through 1 or 2 walls in our laboratory suite. We get these very complex waveforms. And so the idea is if you can measure those waves, and they're different at different receivers, even spaced by a few centimeters apart. So what you can do, though, is you can measure these waveforms. We can generate these either photonically or with pure electronics instrumentation. We'll make a time reverse version of this. We'll transmit it, and it should self-compress. And it should self-compress selectively. So since these waveforms are different, you have to pick one, and that's the one that compresses. The other one sort of remains a noise-like. So you can imagine, this might improve bandwidth or signal to noise for desired channel in a selective way so that you can have privacy compared to an eavesdropper or another antenna receiver listener who's nearby. So here's some experiments. This is with optically generated RF waveforms. These are impulse responses seen at 2 different antennas, about 10 meters from the antenna in a different room. And when we make shape waveform compression, compresses one receiver 2, we can make a waveform that compresses receiver 2 another. So it works. Around the same time, after we sort of make the waveforms are quite complex and there's limits more to the objects. But this is like a waveform generator. It's not quite with long areas. So there's a layout for going 2 balls there, and these are waveforms that are with a very clean selective so this is the optic, but the broadband electronics as well. Yeah, so finally, some of the processing for broadband optics is a representative activity that is currently one of the extremely active in the current research. We'll talk about the frequency entanglement. So this is a very high level introduction. So Quantum when we go quantum, we talk about qubits. The difference is that the coin as an analogy, the coin can flip together tails. So we'll call it a 0 1. It's one together. Mechanics, the experiment, you have the coin in state as the superposition as in tails, right? Or superposition of the 0 and 1 state. It's intrinsically random when you get the 0 or 1, but you know, so these amplitudes tell you something about the relative probabilities of the results. And in fact, there's phase when we write this. The phase matters. We can have quantum interference phenomena. You know, somehow in the classical coin, there's no sense of phase in describing is it heads or tails. Okay, so we'll be interested in that. In our experiments with optics, we're interested in we're going to do this with optical frequencies, and not just 2 frequencies, but many frequencies. And so you might sort of think about, what about a quantum mechanical dice, for example? The die have 6 different sides, so it could be a superposition of 6 different, you know, possible outcomes or higher. And, you know, of course, in modern wireless or optical communications, it's common to have multi-level communications, not just binary. This quadratary amplitude modulation constellation diagram, you know, more than 1 bit per symbol. We're going to be interested in systems that might allow us to store more than 1 qubit, you know, per photon. So we'll call these qubits for higher dimensionality. So we're also interested in entanglement. You know, entanglement is viewed as really the key resource in most quantum algorithms for quantum computing and in most types of quantum communications. And so here the analogy is think of coins again. We'll talk about 2 parties, Alice and Bob, which, you know, may be distant from each other. And if we give them both coins, they can flip their coins. And classically, Alice gets a heads or tails, Bob gets heads or tails. Those are random, but they're independent events. We call those separable. In the quantum system, we could have a system which is entangled, where, for example, one entangled state might involve Alice and Bob both having heads, or Alice and Bob both having tails. Okay, so we don't know which, but their outcomes are correlated. Okay, so if Alice flips her coin and measures a head, then Bob is going to as well, and likewise for tails. So here are these correlations can be non-local, meaning they persist at a distance. Phase is going to be very important, as we'll see. And so we'll talk about this. And this is not limited to coins. I mean, it can be multi-level systems or qubit entanglement. All right, so we're going to be interested in optical frequency with quantum light, and why? Well, partly, you know, it's fairly obvious that we have a lot of tools we've developed for dealing with broadband optical frequency and time frequency, you know, transformations. But technologically, we're all familiar with how remarkably successful WDM transmission over optical fibers that uses multiple frequencies. And so this, you know, really, you know, tells us the frequencies are that just something could send, you know, very robust way over optical fibers. And so if you want to get involved in quantum networking or distributing entanglement over a distance over the fiber network, you know, frequency is a natural, you know, which before our work and a few other groups a few years ago, Roberto Marandotti's group at IRNS Canada is a prominent example. There wasn't much work in this area, but, you know, now it's becoming more and more active. So this is going to be have potential for high dimensionality, as you'll see. We can use classical tools that are known in the classical world. We can perform routing based on optical frequency, some parallel processing ideas that we work on, but I don't have time to get into here. You'll see there's interesting potential to move towards integrated photonics, and there's even some new applications I'll touch on briefly if I don't run out of time about, you know, delay sensing with entangled photons at the 1 picosecond level. Now, an important point is in classical WDM, the different frequencies are independent data channels. They're really independent to relative phase, doesn't matter. So we can say frequencies used to delineate different channels. In the quantum world, there's you know, certainly some ideas which others and we work on that are similar to WDM in that respect. But here what I want to talk about is the case where the quantum information is encoded coherently and entangled coherently across different frequency slices. So we're really going to be interested in kind of the global phase of multiple frequencies with our quantum light. Okay, so how do you make these entangled photons? One technique that's spontaneous parametric down conversion. It's been really a workhorse of time energy entanglement quantum optics for about 30 years now. But the idea is you send a light into a nonlinear crystal. We use Piplin waveguides. And the idea is your input light is at 2 omega naught. We call that the pump frequency. With some small probability due to the nonlinearity, this photon will break into 2 photons called signal and idler. Their individual frequencies are random, but they have to conserve energy. So the sum of the frequencies or the energies matches that of the pump photon. So if we look from the frequency correlation point of view, if we measure these 2 photons, their frequencies, any photon by itself has a random frequency over some bandwidth that can be typically enough to fill the C-band, many terahertz. So they're both random, but they're highly anti-correlated, such they conserve energy. From the time domain, this doesn't happen very often, so we can say the timing of these events are random. Okay, but that's true for either signal or idler by itself. But they happen at the same time in a highly correlated way. So we plot their arrival time of the 2 photons versus time. It's also tightly correlated. And it turns out there's a Fourier transform relationship, and this is related to the entanglement and a notion of coherent 2-photon phase. Okay, so we're going to look at that, very briefly going forward. Okay. Also, this is an area we got into a few years ago. It's possible to do similar things in unchipped microresonators. We work on silicon nitride. The idea is very similar. Here are 2 pump photons that are in band, sort of add their energies and split to a signal and idler. The other thing is, because it's a resonator, there's only certain allowed frequencies. So we kind of generate these patterns in a frequency discrete way. So we call these frequency bins. Okay, and there's a notion we have these frequency correlations, but there's also a 2-photon phase that we'll talk about. Okay, so giving some ideas, these are just looking at the frequency correlations. These are some of our experiments. We're coming with a single pump frequency, shown here with some strong attenuation, into a microring like this in silicon nitride. We get these additional lines coming up. These are the signals and idlers that are generated in pairs. And the way we can know that is we can take this light, we can use a pulse shaper / router to take a low frequency and a high frequency and route them to 2 different single frequency detectors, single photon detectors. And we look at the correlations, and so if we kind of take matching signals and idlers, the second one to the left and to the right, and look at their kind of the clicks that they make, they get a strong correlation about a nanosecond long, which is sort of the inverse of the line width of these resonators. We can do that for the third one on either side, the matched ones. But when they're not matched, when we take sort of the second signal and the third idler, we get essentially nothing. We plot all these results. The diagonal is showing us the frequency correlations. We can then extend this as it turns out, a smaller microresonator, engineered a bit differently. So now we're generating frequency lines of 50 gigahertz. We can see about 40 of those. Okay, so these are frequency correlations, but they're not yet what we call entangled. And the entanglement means, can we still see correlations in both frequency and time domains? That's related to this idea that if these black lines show the correlations between the different frequency pairs, what about the phase between these pairs? They have some phase coherence. That hasn't been tested. If you ask what that would do in the time domain, we're looking at the delay between these signals, okay? It would give you some interesting beat patterns, sort of like a mode-locked laser, okay? Unfortunately, this is at the tens of picoseconds or faster regime. Single photon detectors aren't that fast. The ones we have, we can do about 100 picoseconds. And so you'd average out and get this black line, which is the same as you would get with no phase coherence. So the question is, how can you probe on a fairly fast time scale, with very low intensity signals, and look for a phase that somehow, the relative phase between pairs of photons, okay? All right, so I'm just going to kind of look at that very quickly, and then we'll conclude. So the idea is that we're going to use phase modulators. Phase modulators, you have a periodic RF signal, drives a phase modulator. It gives you frequency sidebands. We're going to use those to mix different frequencies. That's sort of the principal challenge with this thing. The frequencies can be tens of gigahertz apart. How can you do interference? Well, we can do it using phase modulators to make what we call a frequency beam splitter, much like a spatial beam splitter, but in frequency. So, showing in this sort of this picture, imagine this is what we call our biphoton frequency comb in blue. What we're going to do is select some of these lines with a pulse shaper, go through a phase modulator, which is driven, either at the spacing of the lines or in this picture at half the spacing. We'll generate some new sidebands shown in green. And these new sidebands have several parent, 2 or more parent photons, okay, on both sides. We're going to use another pulse shaper to grab a signal and an idler of one of these sort of new, sidebands and look at coincidences. And you're going to ask, is this dependent on the relative phase of the input waveform? And we can play with the relative phase, as I've hopefully shown already with pulse shapers. So we use the first pulse shaper to put some relative phase on one photon as a function of frequency versus the other. And we'll look for quantum interference, in these single photon coincidences. So just very briefly, we can do this. This was parametric down conversion. We carved the spectrum into 36 gigahertz separated bins. We grab 2 signals and 2 idlers and 2 signals, and we play with the input phase, and we can make quantum interference. This is on the coincidence counts. Okay? We can do this with different pairs. And so this turns out when you analyze it, this is enough to show that we have entanglement. This could not be a classical separable state. And we can move up, but we've moved up a little bit to 3 dimensions. So we have 3 signals and 3 idlers, and these sort of nicely sharpen up. That was original data. We got some better detectors since then and can do cleaner experiments than we could do originally. Likewise, we can do similar things to the micro-ring resonators. I won't go into detail, but we can see the same sort of interference curves. And so this sort of approximately the same time as the group I mentioned from Canada, Professor Morandati, were the first to really show this. Here's something. Is somebody talking to me? No. Okay. All right. I'll finish up in the last few minutes. Just a few minutes.
His computer, he prefers it to typing and particularly prefers it to.
Sorry.
Nothing. Nothing.
No. Okay. Yeah. Okay. So let me skip this one. But so we can do that. Let me. Those are. Oh well. I'll get through this. Low dimensions. I just wanted to illustrate 2, very recent activities. So what we're going to do now is it's related to sort of entanglement, but I want to illustrate, the ability to go to higher dimensions or more frequencies. So this is something we call a coherently controlled quantum walk in frequency. By quantum walk, we usually think about, flipping a coin and maybe moving to the left or the right, depending on heads and tails, and doing that in a random way. Okay. People have done a lot of quantum walks by sending light into a waveguide integrated photonics and watching its coupling to an array of different waveguides. And it spreads out in a faster way than you would classically with a coin. Rather than diffusive, people talk something about a ballistic type of spreading. So we're going to explore that in frequency. And the idea is we'll start with one of these entangled biphotons with 16 different frequency bins that have this nice frequency anti-correlation that I illustrated briefly before. Okay. Then we're going to use a phase modulator that we use for entanglement measurement. We're going to drive it a lot harder so that we can sort of mix essentially all of these frequencies. And if we do that and then measure the frequency correlations by measuring different signal and idler frequencies and routing them to different detectors, do that one at a time, then our input states we phase modulate sort of spread like this. And so we can see this original anti-diagonal is where our 2 photons have energy that matches that of the pump frequency when you add them up. So now when we get this plot that spreads in diagonal direction, when we spread, that means the total energy is the distance from this anti-diagonal. We can pick up energy or we can lose energy, but somehow the phase modulator transfers energy onto the photon pair. Call this a correlated quantum walk because they spread in the diagonal direction. which means both signal and idler either gaining energy or losing energy. Now, the interesting thing here is that what if we can play with the phase? So what if we play with the phase of the biphoton frequency cone before we do the mixing? Well, we can find phases. This is a simple one where we just have an alternate pi phase shift between the different frequency pairs. We can completely frustrate this correlated, spreading. We stay on the anti-diagonal, but we spread a little bit in the other direction. Okay, and what this really says is, in this situation, whenever the signal photon gains energy, the idler photon loses energy, and vice versa. So we preserve the total energy. Okay, we can understand why this happens, which I don't have time to get into. But the idea is here is that this is kind of a more basic experiment. Ideas about quantum locks are involved in some approaches to trying to do quantum computing. But by playing with the phase degree of freedom, we can really manipulate what happens physically. Okay, the last thing I want to show here is more from a kind of applications perspective, is we can do very similar experiments and derive picosecond or even sub-picosecond type timing resolution, even though, as I mentioned before, the detectors systems are relatively slow, about 100 picoseconds in our lab. And again, this is going to illustrate interesting things happen when you work with high dimensional, superposition of frequencies. Here we have 9 signal frequencies, 9 idlers. They're spaced by 25 gigahertz. We're going to modulate strongly the phase modulators so that we can mix, among these 9 signals and among these 9 idlers. We're going to just collect the central frequencies and look at coincidences. And these have contributions, sort of from 9 different parents on each side. And it turns out, when you kind of work it out, if you ask, well, what if we give a relative delay between signal and idler? How sensitive are we? It turns out we're extremely sensitive. And so in an experiment, for example, we do our parametric down conversion. These little blue and red balls are supposed to entangle the signal and idler that are frequency correlated. We can use our hardware to route them to different directions, to different setups. We put in delay line that we tune in one of these, and now they have their own phase modulator. Okay? Pulse shapers, single photon detectors. We compare the results. So we're really making coincidence measurements with the difference that we separate these two to different phase modulators, and we look as a function of delay. And it turns out this is, as I said, very delay sensitive. We can get these traces that are about 3 picoseconds wide. With the signal to noise, we can resolve probably 10 times better at the few hundred femtosecond level. And so this is a trick that gives you timing resolution much better than that of the single photon detectors. In ultrafast optics, traditionally, such tricks are, fundamental to ultrafast optics. Here it's not ultrafast optics, but it's sort of broadband quantum optics, and we're starting to be able to, devise similar tricks. Why are we interested? Well, one fundamentally, but one in quantum networking where one wants distributed entanglement, synchronization between different separated, setups is going to be very, very important. And so here we're working with optical fiber type of technology. We can, make these measurements with spatially separated detectors. And so we think there may be some opportunities perhaps to complement classical technologies for establishing very, high levels of synchronism in these envisioned entanglement distribution networks. So with that, we've used up the hour slot. We've gone through the material. Basically, I've had a long-standing interest in what I'll call precision, coherent spectral engineering, or pulse shaping of broadband optical signals. This talk illustrates this is useful both in pure optics, but it has interesting analogies with broadband RF, and it doesn't have to be coherent ultrafast, pulses, but can also be broadband quantum optics where different types of coherences come in. And I've talked about most of these bullets. I haven't really talked very much about using it to manipulate optical frequency combs and Kerr combs. That's another active area we're active in and where there's some interesting tie-ins. So I will conclude by, just sort of, thanking many people who have worked with me over the years. This is a photo of, almost current photo of sort of the recent batch of of students and a number of either past or current sponsors who've helped to enable some of this work. So thank you for for your attention. I'm happy to entertain questions you might have.
Thank you, Professor Wiener, for a wonderful lecture. A small doubt, in one of your slides you have shown they are called as the biphotons.
Yes.
May I know why they are called as the biphotons?
Yeah, okay. So why biphotons and why biphoton frequency combs? It's related to the idea that these photons are generated in pairs through these processes I briefly talked about. And those are highly correlated pairs. And so if you were to write the wave function, do the quantum mechanics and write the wave function, you can't write it in terms of just, here's the wave function of one photon, here's the other. It's really a joint wave function that can be written in such a way that includes the correlations between the two, much as I illustrated very, quickly, what if you had entangled coins? And so because you have these strong phase coherent correlations between the different, the frequency structure in these photons, we call them biphotons. We call them biphoton frequency combs because the particular shape involves sort of a series of equally spaced frequencies.
Thank you, Professor Wiener. Now the floor is open for discussion. Students, scholars, they can ask the questions.
Sir, thank you, sir. The talk was really very informative and accelerating. Sir, I have received a few questions. I want to go with the questions.
Okay.
Yeah, please go ahead.
Yes, sir. Okay, so toggling nanolasers on and off by magnetic field has now become possible. Earlier, nanolasers were directly controlled mechanically or with heat or light, which could incur losses in the optical signals, but remotely manipulating them by using magnetic field will considerably reduce the losses. Which other methods, in your view, can be used to reduce the losses caused by external disruptions?
Caused by, what was the last word? External
Disruptions, yes. I mean external factors.
Yeah, okay. Well, so I think within, I think we're talking about the quantum work. And so, often people are talking about disruptions, they're talking about decoherence. So you've got an NV center, or you've got a trapped ion or whatever. And due to undesired interactions with the environment, the phase gets randomized. Okay, so that's sort of a decoherence that everyone is sort of fighting in these matter-based quantum systems. In the work we're doing with quantum photonics, the situation is somewhat different. Photons are quite robust generally. That's a strength and a weakness. It's the strength for propagation, transmission over fibers. It's a weakness if you want to make nonlinear interactions for photons to do C0 gates and so forth, because it's very hard to do just in a pure photonic level. But so it means that photons are not particularly prone to decoherence, unlike the matter-based systems. That's why they're good for transmission. Okay. On the other hand, the loss is very important. And so in our systems, if we build these, phase modulators and systems for manipulating entangled photons, based on phase modulators and other components, in the lab experiments right now, we incur quite a bit of loss, over 10 dB typically. And, for really using this from a technological perspective, what we need to do is reduce the loss. To get there, we're trying to take these systems that are built up of discrete components that are not necessarily optimized for loss, phase modulators, pulse shapers, and trying to put them in integrated photonic chips with an emphasis on doing it in a very low loss way. So, we've been working on this for a year or two. We're just starting to get preliminary results. But, in principle, it looks like you might be able to bring loss down from more than 10 dB to the 2 or possibly even the 1 dB level. I'm pretty confident we won't get that low right in the first run, but we think it may be possible eventually. And so that's kind of a related activity that I thought I would mention.
Okay, thank you, sir. So next question. So you mentioned about amplitude and phase masks. So is it possible to design fractal-based amplitude and phase masks which are which can efficiently replace the conventional masks for efficient signal transport? Fractal geometries such as Sierpinski's triangle, Koch snowflake, etc.
Yeah, so interesting question. Frankly, I have a little knowledge of these special fractal type shapes that were mentioned. But I would say, for this particular application, maybe that's not so relevant. So in the early days, which was like 30 years ago or a little bit more, the first experiments, we made fixed masks using photolithography type techniques and, clean room. And for example, the phase mask would be a piece of glass that had little trenches etched into it by fraction of a micron to give a differential, sort of phase. But those were, quickly replaced with programmable elements. We did some of the early work there, and then others contributed to moving that along. Mostly with liquid crystals. Today, people use liquid crystals and liquid crystal on silicon and MEMS. There's a number of choices to do a large number of programmable pixels. I think for most applications, this programmability is essential. Okay. There's a lot of work going on, as you're probably familiar with metasurfaces, both for manipulating light spatially, but there's an active research area in looking at time frequency, metasurfaces with, time-domain impulses and what the response are. So that might be an area where fractal designs could come in. Though I have to say from, for making, very flat lenses and all other kind of optics, the metasurfaces are great. For shaping pulses, until people learn how to make them programmable, I don't think they're a very good fit. So that's not exactly answering your question, but at least giving some, my personal perspective.
Okay, next question. So why don't we use broadband technology to transmit digital signals and use baseband technology to transmit analog signals?
Why don't we use broadband technology to transmit digital and baseband for analog? Search me. Yeah, I'd say most people, most systems that I know of are transmitting digital signals, period. That's where the field is going. That's what most wireless does, and that's what most fiber optic communication does. It's everything is encoded digitally. Underneath the digital signals, there's fancy waveforms. That's kind of the analog part, but they're done in a way that sort of gives you digital capabilities. So that's probably not answering exactly what you're saying, but that's what comes to mind.
Okay, so next question. In one of the slides, you discussed about shape modulation technique of the pulse. After modulating the shape of the pulse, you made it undergo the dispersive stretch-up. So, won't it cause the pulse to lose its localization due to the dispersion?
Yeah, so you're probably referring to the, what am I doing here? Give me just a second. To the pulse shaper setups. I'm gonna pull one up. Just have to find it. Here we go. Okay, let me share again. Okay, so you should be able to see just sort of a view of a pulse shaper slide where it says, okay, I imagine you can see that now. And, so if I call this a dispersive stretcher, what this is, an interesting point is we've got these grating and lens to spread out the frequencies laterally, okay? But if you put the grating and lens and grating at the right position, essentially you make a unit magnification telescope, you can run this in completely dispersion free way. And so when we do this, this is done in a completely dispersion free way. So if we take out the modulator array or the mask, the output pulse is the same as the input pulse. So, these sort of grating and lens systems are related to the chirp pulse amplifier stretchers and compressors. But in those systems, the gratings are moved to different locations where you can induce large chirps and compensate large chirps. In using these systems in pulse shapers, we prefer to do it in such a way that we can spread out frequencies, we combine frequencies, but keep them localized in time. If we put on some extra phases on the modulator array, then we can purposely reshape the pulses. But if we're not doing that, the pulses spread out, come back together without any temporal spreading. And so that's actually, I didn't mention it, but that's sort of an essential sort of ingredient. Okay.
Okay, so our next question. So when we talk about information signal transfer, there are some external losses creeping into the main information signal. For quantum information transport, what sort of losses we have to deal with?
I don't have a really good answer there, but as small as possible. Generally there's trade-offs. So if we're looking at what people call discrete, quantum discrete encoding, and so it really means we have binary or higher information. We're kind of counting photons in the end, and so the loss basically reduces the flux of photons and of coincidences. So there isn't sort of a set loss that you have to live with, but the more the loss is, the lower your rate of getting successful events. So you clearly want to minimize the loss. You're doing what's called continuous variables. Okay, discrete variables, continuous variables. That's like squeezing. There are thresholds. I can't recite them to you, but there are theoretical thresholds of how the loss has to be and how much squeezing you need to carry out general purpose tasks.
Okay, sir. So I have a question. In one of the ending slides, there was splitting of the spectrum. The spectrum was split into two spectrums, and those were directed towards the event timer. So how was it modulating the event timer? I did not get that.
Yeah, let me see if I can. We're probably talking about this one.
Yes, sir.
Yeah, okay. Right, and so the idea here is that what we can do with these pulse shapers is, as I described, we can put on a frequency-dependent phase, frequency-dependent transmission. We can also, the modern pulse shapers, I think I neglected to describe this, it also inherits some wavelength selective switch capability, which means you can actually, on a frequency by frequency basis, program which output fiber they go to. And these can be configured with 2 or more output fibers. And so what we do here is we choose one of the sort of high frequency parts, I guess, of the photon and one part of the low frequency part. We can grab which frequency bin we want of each one and send them to different fibers. And those then impinge on different single photon detectors. And what the event timer does is it keeps track of when a kind of a little pulse, a little click comes in, and allows you to keep track of the relative timing. So that's how you say you have a coincidence. Did you get clicks at the same time within some small window that you define? So I hope that helped.
Yes, sir. Thank you, sir. So that brings us to an end of the event. I would like to thank Professor Wiener for being with us here. Okay, sure.
Thank you once again. Saurav, you kindly take over.
Yeah, is there this ultra fast optics? How it is can be applied for the terahertz photonics? You told that RF photonics. Is there any relation between terahertz photonics and this ultra fast optics?
Okay, yeah, thanks. So certainly, there's different ways to make terahertz signals. Now, these days, one way involves very long wavelength quantum cascade layers. That probably has not so much to do with ultrafast optics. But since probably the late 80s again, researchers started sending short optical pulses at fast photoconductors coupled to antennas to generate ultrafast electrical or really terahertz radiation. And so, many of these, any kind of time, what people call time domain, terahertz systems, time domain terahertz beams, time domain terahertz spectroscopy, ultra-short pulses are used to create the radiation through hitting a very fast photodetector with a short pulse, and are also used on the detection end to either interacting with another photoconductive detector or with electro-optic media, for example, to make the measurement of the ultrafast radiation. So there is, it's or at least the time domain branch of terahertz photonics, a very close relationship.
Okay. Thank you, Professor. So, any questions? Any more questions, Avinav?
Yes, sir. Good morning, Andrew, sir. This is Avinav Arun.
Hi.
Yes, sir. So my question was for your experiment of this frequency beam entanglement. What was your source emitter? What was the component that you use as the source emitter?
Give me just a second here. I'll be with you in a second. Okay, not sure. Never mind. I'll take one or two more questions. I've just got another virtual meeting coming up, and I was going to alert the people, but I'll take one or two more questions, and I have to move on to that. So for these entangled photons, I think I can move back to this fairly quickly. We use, where is it? Two types of sources, shown here. So either we use second order nonlinear crystals. In our case, they're periodically pulled lithium niobate waveguides. So we just pump it with a red light around 780 nanometers, 775 nanometers. And the phase matching is engineered such that out comes now two photons, both in the telco band. Okay. The other thing we do are we use microring resonators and integrated photonics. Our experiments so far have been confined to high quality factor greater than 1 million, sometimes quite a bit more. Micro resonators based on, in silicon nitride on top of the silicon substrate. And those work through a third order nonlinearity or spontaneous Fourier mixing, but otherwise similar to the other sources. So those are our two types of sources.
Thank you, sir.